A new interstellar object is racing through our solar system.
We should check whether each and every object that arrives.
It came from beyond our solar system, silent, glowing, and unlike anything we've tracked before.
What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
But what if that light wasn't reflection, but radiation? Harvard's Avi Loeb says it's not a comet. It may be something built by aliens, an artifact adrift between stars, and it might be watching us. A beacon where none should be. It was supposed to be a comet. That's what the initial trajectory suggested. An icy interstellar object flung in from the cold reaches beyond our solar system. NASA's Hubble Space Telescope locked onto it. Telescopes adjusted. Researchers waited for the telltale signs. A long dust trail, ice sublimating in the sun's heat, a bright reflective coma. But that never came. Instead, what Hubble saw was a compact, luminous glow, not trailing behind the object, but positioned directly ahead of it, facing the sun. Not a tail, not a reflection, but a beacon. A bright patch of light burning in the one place it shouldn't be. It was wrong. The laws of comet behavior didn't apply. This wasn't light being scattered across grains of dust. It was light that looked generated, as if from a power source. Even stranger, the glow didn't fade gently at the edges. It dropped off sharply, no blur, no slow transition. Just light, then darkness. At first, astronomers offered conventional explanations: dust, ice, maybe an unusual reflective angle, but none of them fit the profile. The object's brightness didn't behave like anything powered by the sun. That's when Avi Loeb, the Harvard astrophysicist who once proposed that another interstellar visitor, Oumuamua, might be artificial, stepped forward again. His theory? This wasn't a natural glow at all. It was a nuclear signature, and if that's true, then 3I Eta Luce isn't just a visitor. It's a warning light, blinking in the void. The stranger that defied comet logic. Comets are among the most predictable drifters in the cosmos. When they near the sun, solar heat causes ice to vaporize, creating a hazy coma and a long, graceful tail that always points away from the sun's direction. That's Comet Physics 101, and for decades, it has held true. But 3I/ATLAS broke those rules. As Hubble tracked its motion, scientists noticed something disturbing. There was no tail, no streaming trail of particles pushed by solar radiation, just that compact, forward-facing glow. Even stranger, the way the light faded outward from the object made no physical sense. Instead of a slow, natural drop in brightness, the light fell off suddenly, like a cliff. One moment, intense glow. The next, near complete darkness. That sharp boundary was unlike anything researchers had seen in naturally evaporating comets. There was no soft gradient, no dusty veil, just light, then none. One observer described it as more like a flashlight beam than a comet's halo. The implications were unsettling. For dust to scatter sunlight in that precise pattern, the object would need a very specific and extremely large surface area, positioned just right. But that wasn't what the data showed. The conventional physics couldn't explain it. The object wasn't acting like a comet. It wasn't behaving like a natural rock. Every model NASA used to simulate its brightness and trajectory began to fall apart. That's when Loab posed a new question. What if it's not reflecting anything at all? What if it's glowing from within? The James Webb Telescope's unsettling glimpse. When the James Webb Space Telescope turned its infrared eye toward 3IA T-LUS, the results didn't solve the mystery, they deepened it. Webb's spectrograph peeled back the glow and found a chemical fingerprint unlike almost any comet on record, a coma rich in carbon dioxide, but strangely poor in water. One of the highest CO2 to H2O ratios ever measured. In cosmic terms, it was upside down, like a campfire that burns with smoke but no flame. That imbalance hints at an origin far from what we know. Perhaps 3IA T-LUS formed on the frozen edge of a protoplanetary disk where only carbon dioxide could solidify. Or maybe it was scorched by radiation so intense it rewrote its chemistry, stripping water away and leaving a husk of exotic ice. And Webb revealed something else. This visitor isn't just unusual, it's enormous, roughly 3.5 miles wide, making it the largest interstellar object we've ever seen. A relic older than Earth itself, drifting in from a place we cannot trace. But even those revelations, the alien chemistry, the vast scale, couldn't account for the light. Webb confirmed what Hubble first suggested, a glow too compact, too abrupt, too deliberate, a glow that refused to fade the way nature demands. The strangeness was no longer just a matter of physics, it was written into the comet's very composition. The Manhattan-sized illusion. If 3IA Tellus were just reflecting sunlight, its brightness meant one thing: it had to be huge. Based on standard reflection models, NASA initially estimated the object to be nearly 20 kilometers wide. That's roughly the size of Manhattan. An object that large passing through our solar system should be extraordinarily rare, perhaps once every 10,000 years. And yet, here it was, silently cutting across our skies. But that size was an illusion. It only made sense if sunlight was the source. Loab and his collaborator, physicist Eric Koh, took a different approach. They analyzed the light profile, not just how bright it was, but how it behaved as it spread outward. What they found was a brightness pattern that didn't match reflected sunlight at all. Instead, it matched what you'd expect from a centralized internal energy source, something glowing from the inside out. If the light wasn't being scattered across a giant surface, but emitted from a tight core, then the object didn't need to be the size of a city. It could be smaller than a football field, shrinking from a city to a stadium in scale. That single shift rewrites the story, because a compact object glowing with such intensity defies the limits of natural law. Because if an object under 100 meters across is emitting 10 gigawatts of power, it's not just bright, it's impossibly dense with energy. That kind of output from something so compact doesn't exist in nature, not without nuclear fuel or engineered intent. A comet this small shouldn't shine this brightly, unless, of course, it isn't a comet at all. Shadows of the atom, a nuclear core? The scientific method demands skepticism. So, before declaring the presence of a nuclear engine inside an interstellar object, Loab asked a simple but necessary question. What else could it be? He began eliminating possibilities, starting with the most exotic. Primordial black holes, theoretical remnants from the early universe, are known to radiate faint energy via Hawking radiation. But the numbers don't lie. A black hole of the right mass would emit just 20 nanowatts, less power than a refrigerator light bulb. The glow from 3IA Tellus was 10 billion times brighter. Next, Loab considered something more plausible: supernova debris. Radioactive chunks ejected from dying stars can glow for thousands of years. It's a real phenomenon, uranium-rich meteoroids glowing with residual heat. But the odds are vanishingly small. The amount of radioactive material needed to sustain 10 gigawatts of output is enormous. Not only is it rare, it would have to arrive here, now, by sheer cosmic coincidence. And then there's the default explanation: melting ice and vaporized dust, the standard comet playbook. But Hubble didn't see the smooth coma that forms from outgassing. It didn't detect a steady slope of fading particles. It saw a cutoff, a glow that behaved like an engineered spotlight. No fade, no plume, just an emission. One by one, the natural explanations collapsed under their own math. So, what's left? Loeb's final proposal is the most controversial and the most logically consistent with the data. What if 3IA Tellus is powered by a compact nuclear reactor? Not a rock, not an accident, but a machine, a spacecraft, a probe. In that light, the glow isn't a mystery, it's a signature, the radiation of purpose, and the object's path. That might not be random either. A trajectory that watches back. Objects from interstellar space don't usually fly clean. They tumble, drift. Their orbits come in messy, chaotic arcs, flung by gravity, steered by nothing. But 3IA Tellus didn't behave like that. Its path was smooth, efficient, and, in Avi Loeb's words, fine-tuned. It entered our solar system on a trajectory that almost seemed calculated. First, it passed near Earth, but just as it reached its closest point, the sun moved directly between the object and our line of sight. For crucial hours, telescopes were blinded. Then, it veered past Mars, just within the reach of our rovers and orbital satellites. After that, it skimmed near Jupiter, our largest planet and gravitational anchor. 3 planetary flybys, 3 points of interest, 3 chances to observe, or be observed. To Loab, this wasn't coincidence. If 3I AT-LUS were a scout, its route made strategic sense, passing close to the solar system's key players, while remaining just distant enough to avoid detection. It was as if it had studied our neighborhood before entering, and chose a path we couldn't follow. And here's the part that unnerves: the timing. If this object had entered just a few months earlier or later, its trajectory would have missed Earth entirely, but it didn't. It came close enough to see us, close enough for us to see it, briefly, before it vanished back into the dark. An accident? Maybe. But if it wasn't, we weren't just witnesses to 3I AT-LUS. We were the subject. The reckoning? If this is real. If Avi Loeb is right, if 3I AT-LUS is not reflecting light, but producing it, then it isn't just an interstellar object. It's an engineered source of power, operating in deep space. That possibility demands more than curiosity. It demands preparation. Because if something is emitting 10 gigawatts of sustained energy, the same as 10 full-scale nuclear power plants, then we're no longer observing a passive traveler. We're studying a power source of immense potential and unknown intent. To understand the danger, we don't need to imagine futuristic weapons. We already live in a nuclear world. A single reactor meltdown at Chernobyl rendered hundreds of square kilometers uninhabitable for generations. Fukushima, decades later, reminded us that even peaceful energy can become a devastating force when containment fails. Now, imagine a compact reactor hurtling through space, untethered, unmonitored, and possibly designed to maintain output under extreme conditions. Loeb's estimation that 3I AT-LUS emits enough energy to match Hiroshima's blast every few seconds isn't poetic exaggeration. It's physics. That power, if directed or focused, could disable satellites, blind sensors, and wipe out communication networks in moments. And if targeted at Earth itself, the consequences wouldn't resemble an impact event. They would resemble a coordinated strike. We've seen how natural disasters from space can rewrite history. In 1908, the Tunguska event flattened 800 square miles of forest without leaving a crater. That was a random rock, a chance encounter. But if this glow in space is something built, something aware, then we're not talking about chance anymore. We're talking about intent. And in that case, the question we should be asking isn't, what is 3I AT-LUS? If the glow of 3I AT-LUS was not reflection but intention, then it was more than light. It was language. A beacon where none should be, written in radiation. Brief, deliberate, unforgettable. The universe may not be silent. It may already be speaking.